Chapter 3, Telescopes and the Instruments of Astronomy. Take a look at that picture. That's one of the best places in the world to do astronomy. Where do you think that's located? Well, it might surprise you to know that that is Hawaii. That's on top of Mauna Kea in Hawaii. Probably the second most prominent place in the world for astronomy. Currently, it's about tied with Chile for that honor, but Chile is about to move way ahead of Hawaii in terms of the total number of telescopes and things like that. Soon, Chile will have 70% of the world's large telescopes in terms of area of the mirror. But anyway, I'll talk more about that later on. I've been to Chile and experienced that, and I have yet to go to Mauna Kea, so I definitely need to check that out. But what they have in common is high elevation and super dry climate, and we'll talk about why that's so important later on. First, let me just mention that astronomy, as you can see there, is a little different than, let's say, pure physics. In physics, you tend to have a theory come out, like, for example, the theory of relativity, and then you make observations that either support that theory or they don't. So in the case of relativity, it actually took the technology decades to catch up with Einstein's theory. The theory was so far out in front of their ability in the early 1900s to actually observe these things. I mean, Einstein was predicting things like gravity waves that we just now detected, in like 2016 or whenever, 2017. So, in that case, the theory is way, way ahead of observation. But in astronomy, it's almost always the reverse. The observation comes first. We see something interesting in space, and then the the theorists have to scramble and try to figure out what they're looking at and what caused that. Now, guess how you make better observations? You get bigger and better telescopes that cover a broader range of the spectrum. That's how it's done. I don't know of any other field that is so closely intertwined with technology than astronomy. Every time you build a bigger and better telescope, you learn new things. It just has always been that way since Galileo first pointed his telescope to the skies in 1609. Anyway, so to give a couple specific examples where observation was ahead of theory in astronomy, the first extrasolar planet discovered around a sun-like star was wildly different than anything they expected. 51 Pegasi b wasn't supposed to exist. It was so different than what they expected. It was about like finding a unicorn in the forest. And immediately the theorists had to change their whole concept of how a large planet, because it was a very large planet located very close to its star. They didn't think that could exist in 1995. But anyway, another great example is in 1998 when they observed that the universe is accelerating. I mean, nobody predicted that. That wasn't supposed to happen. But again, ever since then, the theory's trying to catch up. What is this mysterious energy causing the universe to accelerate, what we call dark energy? We still don't know at the time of this recording. All right. So to get better observations, you need better equipment. And as you can see, telescopes have gotten bigger and better, much more complex than in the days of Galileo and Newton. And now they cover the entire spectrum, and that's a huge factor as well that we'll get into in this chapter. But let's go back to the original type of telescope, an optical telescope, just like you see there in the picture. Those are actually Galileo's handmade telescopes. So the question is, first of all, what is a telescope? Well, this is my favorite term for it, a light bucket. It's a light bucket. It collects light. Just like you'd collect rainwater, a light bucket collects photons. And then you notice the definition continues, and concentrates them. So you need a way to focus them and then analyze what you're looking at. That's what a telescope is. It collects the light and then it focuses it. And we'll talk about the various types of telescopes as we go along. So right now we're talking about visible light, the light that you see with your eyes, the original type of telescope that was first used for astronomy purposes by Galileo. He didn't invent it, but he did first use it for astronomy. Now, the type of telescope that Galileo used, the first type ever invented, was called a refractor. A refractor uses a glass lens. And a glass lens has some issues. There's some good and some bad points, but it's very, very simple. You basically have, if you take a look at the picture here, the lens at the front of the telescope is called the objective lens. All right. And you want the biggest lens possible. It's like having a larger eyeball to collect as much light. You notice the lens actually, as the light rays pass through it, they converge and they actually switch, which makes the image upside down. A lot of my students, first time they look at our finder scope of our telescope, they're surprised to see everything upside down, but that's why. And then the light rays, as they're diverging here, you need an eyepiece there to sort of straighten out the light and magnify it. And that's it. You have two pieces of glass. You have an objective lens on the front and an eyepiece on the back, and that's all there is to a refractor. It's very, very simple. Now, this is one of the largest, I think it is the single largest refractor ever made, but it was built back in 1898, the Yerkes Observatory in Wisconsin. And as you can see, it was super long focal length. That's why they had to make it that long. And the problem is making a large piece of glass like that, it gets very difficult to support it. It gets very, very heavy. This one had a lens that was 1 meter wide. That's the largest one ever made. But it turns out there's something better. We'll get to that in just a moment. But first, that's the Yerkes at 1 meter. There it is. I'd love to visit that, actually. I haven't been there yet, but I'm sure I'll check it out sometime. All right. But there's a design that's better, at least for large telescopes. Now, refractors are still fine. We have a refractor in my class. I love it. It's great for astrophotography because the air is kind of trapped inside and it doesn't, it's not as wavy. You kind of have control there, and it's beautiful for astrophotography. So I absolutely love our refractor. But for making really large telescopes, turns out that reflectors are easier to make, better to make. First of all, I didn't mention this, but refractors have a problem called chromatic aberration. They tend to, so you have to have like a double lens in there to counteract that, so you don't get this sort of smear of colors that you don't want. That's a problem when Galileo first started using a telescope that they had some issues with. But along comes Isaac Newton and says, hey, let's try using a mirror. And the first obvious benefit of that is that there's no chromatic aberration with a mirror. All different frequencies of light, all colors bounce off a mirror the same. No problem there. Now, Newton did have a problem with this. He had to know, where he was going to send the light. So here's the light comes in. If you look at the upper left there, the light comes in, hits the primary mirror, bounces to a secondary mirror. That was Newton's solution to bounce it out to the side. And anytime you see a telescope then with an eyepiece on the side, it is a descendant of Mr. Newton's design. So a Newtonian has the secondary mirror on the side. I think we have a small Newtonian in class, but what we really have a lot of are Dobs. You can get a really big telescope, really large telescope, large mirror for a relatively small amount of money with a Dobsonian. Now, they're not good for things like photography, but they're handy just because they're easy to use. Now, a Dobsonian is just a subcategory, as you can see, of a Newtonian. It still has the eyepiece on the side. Everything's the same. It's just that it's on like a swivel base instead of their traditional tripod. So that's what we call a Dob, or a Dobsonian, and we have a couple of those. All right, but there is another way to handle having light bounce off that mirror. The other solution is to actually have it bounce off the secondary mirror right back through the main mirror. This is called a Cassegrain design, and you have to have a hole in your primary mirror. I'll show you here at the bottom. There we go. So take a look at the bottom. The light's coming in from the left this time, comes in, bounces off the main mirror, bounces off the secondary mirror, and then right back, instead of bouncing out the side, it bounces right back through a hole in the primary mirror. And it turns out that's really not a big problem or anything. That's not a big issue. Cassegrains are wildly popular. We have one in our little dome that we built in our school garden, and I'm really thrilled with it. It's very versatile, and it's nice for a little bit of everything, for astrophotography, for example. Very popular. So we're inside the 4-meter telescope at Cerro Tololo. We just watched a beautiful sunset, and check this monster out. Look at that. What you're seeing up there is I believe it was a was a wide angle. They're using that to study dark energy, what's causing our universe to accelerate. Cutting edge, best stuff out there. It's being done right here. We spoke to a man earlier that's a professor from Brown University, and he was looking at dark matter and galaxy clusters. So just incredible. And the view from up here, amazing. This thing is so mammoth. All right, so that was me. I forgot that I put that in there. That was me in Chile at one of the largest telescopes that I've had the pleasure and the honor of getting to visit up close, the Blanco telescope. That's a 4-meter wide mirror. And then you notice at the focal point where the light comes in and bounces off the mirror, they have a camera there, a very expensive, very large camera. And so it's able to do some cutting edge work. We'll talk next time. Yeah, I better wrap it up. We'll talk next time about the size of telescopes, which is a very interesting discussion, and then about the resolution, how sharp of an image that you get. Thanks for listening.